Hello, everyone. Good afternoon, good morning, wherever you might be. I'm Giulio Boccaletti. I'm the scientific director of CMCC. We're going to just wait a minute for folks to join, and then we'll get going. If you've joined us, it means that you know that we're going to talk about GraphCast, learning skillful medium-range global weather forecasting. So I'm sure you're in the right place. Let's just give us another 30 seconds, and then we'll get going. If anybody's just joined, we're just waiting for 30 seconds for folks to connect. We have a rather full house, if one can say so, for a digital medium, and so just making sure that everybody can join. My name is Giulio Boccaletti. I'm the scientific director of the Euro-Mediterranean Center on Climate Change. Right, I think we can get going, Remi. So I'll do the introduction, and I'll start just by making sure that you guys know who is hosting, so that we set the stage here. I'm delighted to be facilitating this conversation with Remi. It's a great pleasure to have him with us. Just to orient us to who CMCC is, just make sure, there we go. We're a global scientific institution focused on the study and modeling of climate change and its effects on society. You can see our mission on the right-hand side. I will not read it today, just to make sure we preserve some time, but we are a proud European institution that deals with all aspects of climate and climate change. We are organized in 3 research institutes, so if you have interests in any particular area, disciplinary area of climate change, you can probably find something of interest in our institutes, an Institute for Earth System Prediction, one on climate resilience, and the European Institute on Economics and the Environment. We also are one of the principal supercomputing centers in Europe, fully dedicated to climate research, and one of the largest supercomputing facilities in Italy. And we make use of this all across the disciplines, from Earth system modeling all the way to economic modeling. We are proudly Italian, so we have several offices. Do come and meet us. These are all lovely places to visit. So I encourage you all to get in touch. And we are, in fact, a foundation, but we're a foundation of proud research institutions, a number of Italian universities, the INGV, the National Institute for Volcanology and Geophysics, and Resources for the Future, the environmental economics outfit out of the US. And with that, the only other thing I should tell you is that you will be listening to Remi, who I'll introduce in a second. You will have a chance to ask some questions, which I will have the good fortune to moderate at the end here. You have 2 options. One is you can raise your hand. Because we have several hundred people, that may not be the most expeditious way of asking the question. It is probably best that you ask your question in writing through the Q&A facility that's at the bottom of your screen. You can ask a question, and then at the end, depending on time, I will make sure to get to as many as we possibly can. All right, and with that, it is my great pleasure to introduce Remi Lam. Remi is a computational engineer, has a background in fluid mechanics, I would imagine, as a graduate of MIT, and has been at Google DeepMind for several years now, almost 6 years. And as you probably all know, and that's probably the reason you're here with us today, there's a revolution going on in Earth system science, and certainly meteorology, around the use of empirical models and machine learning and AI. And there is no question that Remi is the right person at the right time in the right place. And so he's published a very influential, well, a number of influential papers, the most recent of which is the one that he's going to talk to us today about, which is using GraphCast. So with that, I pass it over to you, Remi. Thank you so much for accepting the invitation, and we're looking forward to your talk.
Thank you so much. Can you hear me okay? Yes. Okay. Thank you for the invitation. It's really my pleasure to present some of the work we've been doing in the past couple of years to you, get some feedback, hear what you think about that, and also like what you think is maybe the next step and how this can be more useful in the future for the type of research you're doing. So Yeah, thank you, Giulio, for the introduction. So I'm Remi. I'm a staff research scientist at Google DeepMind, and I'll be talking about like how to make global weather forecasting with machine learning, and especially about GraphCast. If I have a little bit of time, I may touch upon like the new type of model that we're working on and that we've kind of published as a preprint, but we'll see how much time we have, and I definitely want to take time to take questions. So yeah, the paper that I think many of you have seen is like this paper about GraphCast, learning skillful medium range global weather forecasting. I'm presenting on behalf of this team. Many people at Google DeepMind that work on that project for a year and a half, 2 years, and the paper was published in Science very recently. I hope you got the chance to read it. And the appendices, we put a lot of effort to like really go into very advanced or force advanced evaluation. So there's a lot of really good information in there. I would encourage you to have a look in case you're curious, and give us some feedback. And without further ado, what were we trying to do really with GraphCast? The goal was to improve global weather forecasting with machine learning. And what GraphCast does is it predicts the Earth's surface and atmospheric weather up to 10 days ahead in high spatial resolution. And by high spatial resolution, we're talking about quarter degree spatial resolution. So this is how the data is laid out. I don't really have to show that to you, but I just wanted to start by showing like a few examples of the variable we're predicting and what they look like when we predict them over 10 days by 6-hour increments. So you have the surface wind on the left, the surface temperature in the center, and temperature at 500 hectopascal on the right. And this is just 3 out of 227 weather variable that GraphCast models and predict over time. The reason we're working on this project and the reason we try to apply machine learning to that is that we believe this could bring a paradigm shift in weather forecasting. So far, the way to improve the model, as far as I understand it, is to really like put more compute into scaling the existing algorithm that we have that solve PDEs, improve the modeling, improve the subgrid scale parameterization. So there's a lot of clever work happening here, but the major bottleneck is the compute. Like by using bigger computer, we can make better forecasts, at least for medium range. One thing that is not so straightforward to use in that paradigm is the large amount of data that is now becoming available. And so what machine learning brings to the table is basically saying like, okay, maybe we can keep the compute like fairly reasonable, but we can push on the axis of data, use more and more data, leverage more and more data. And maybe that's the way we improve the forecast rather than pushing on the compute axis. And this works, uses certain type of data, reanalysis data, but I'm sure like in the future we'll see like plenty of different works that leverage all of the wealth of weather data that is nowadays available. So some of the key points of the paper, GraphCast significantly outperformed the industry deterministic gold standard for medium-range global weather forecasting, which is HRES, the model developed by ECMWF. It's also like able to better support certain type of extreme events, and I'll go into some details about that. And one thing that is, I think, quite key is that it's much faster and much more accessible to make weather prediction nowadays. We've released the code. It's on GitHub. The weights are also publicly available. So it really makes it it lowers the bar for people to kind of take that kind of model and try to make their own prediction and adapt the model to whatever use they're interested in. So just to give you a sense of like the data which we're working with, which for machine learning problem is quite big. So you can see here, let me grab a pointer. This is like kind of standard data set, like historical data set that people have been using in machine learning, like the MNIST, so digital, basically trying to recognize digital handwritten digits in images. Like that's pretty small. Image data was much bigger. Like, so those are like kind of typical academic data set that people were using, I think, back in the days in machine learning. And this is like just one variable of ERA 5 at quarter degree latitude, longitude resolution. So GraphCast works at that resolution, so quarter degree resolution. So that's roughly 1400 pixel by 700 pixel. So that's roughly 1 million points. We're predicting 6 atmospheric variables at 37 levels of pressure level, plus 5 surface variables. So that's 227 variables we are predicting. So that's 227 instead of the 3-channel RGB for a normal image. And then we're trying to make a 10-day prediction by increment of 6 hours. So that's 40 prediction in a row. That's pretty huge. When you think about a 10-day prediction, just of that data, it's 35 gigabytes of data, just the data itself. And so when you think about like the accelerator on which machine learning models are trained, For instance, if you the type of machine that we work with, there's 32 gigabytes of memory to do not only use the data, but also train the model, compute the activation, and so on. So really a big part of the challenge in applying machine learning to weather is just the sheer scale of data that we have to deal with. So why now? I think there's multiple factors. One is around data. There's like this, we're not starting from scratch. We're kind of building we're standing on the shoulder of giants here, because we're using like the ERA5 reanalysis dataset that was computed and made publicly available by ECMWF. So it's really a lot of data, more than 40 years, at very high quality data and quality control data. We have a lot of compute nowadays that is available with very specialized type of hardware for machine learning that makes quick learning and quick inference. By inference, I mean prediction. And then we have also a very large class of powerful deep learning algorithms. So in this work, we use graph neural network, but we've seen a lot of work popping out in the past couple of years using CNNs, graph neural network, FNOs, transformers, and so on. So there's really been a lot of work in that space recently, and I think that was really like kickstarted by that benchmark called WeatherBench that really put together kind of the weather aspect with the machine learning aspect into like one kind of challenge that people could try to tackle. So this is like kind of the landscape of where we were like maybe a couple of years ago or a year ago. And so what we designed was this algorithm or this model GraphCast, which you can think a little bit of a learned simulator based on graph neural network. But I think it's more than a simulator in itself, and maybe I'll based on the question, maybe we can go into that a bit later. But how does it work? So GraphCast takes as input a weather state, a full description of the state of the atmosphere, so the 6 variables that I mentioned, some of the surface variable, and then also some terms that are called forcing terms, essentially. Actually, technically, it takes 2 of those states as input, but for the purpose of explaining, I don't think it's really necessary to have that detail in mind. So that input is fed into GraphCast that predicts the next 6 hours state. And there's like 3 parts in GraphCast. There's the first one is an encoder. So we have data that is laid out on a latitude-longitude grid. And then for each of these points, there's multiple physical variable on multiple vertical levels. So the first part is the encoder, which essentially maps those physical variables on latitude-longitude grid into a latent representation on a mesh. And I'll explain a little bit what this mesh looks like. But it's learning a representation. And when the data arrive at this point, it's not anymore a physical variable. There's no temperature. There's no pressure or something else. It's like something learned completely by the algorithm from the data. Then the second part is a processor, which takes those latents that have been learned and process them on this complex structure that we call a multi-mesh. And finally, once that has been processed, there's a decoder that takes those latent representations that have been processed and kind of convert them back into something that is interpretable on a latitude-longitude grid in terms of physical variables. So we get back to temperature, etc. So what is this complex structure in the middle that we call multigraph? It's not that complicated in the end. It's just we start by a graph, a very simple graph that is called an icosahedron. That's the structure that you can see here on the left, M0. And this has 20 faces, 20 triangles. And the nice thing about this structure is that you can kind of refine it in an automatic way that is very easy and very amenable also for processing afterwards. So you can see that you can refine this icosahedron by taking each triangle and refining it into 4 smaller triangles here. You can see here. So that's M1. And so you could do that iteratively, M2, M3, up to M6. That's what we're using in GraphCast. And the multi-mesh is the collection of all the nodes in that really fine mesh here that is approximating a sphere, and the collection of all the edges generated by the intermediate stage. So you have very small edges that are able to capture very local interaction. And at the same time, you have those very long edges that are able to kind of transport information across the globe very efficiently in very few message passing steps. So that's how we managed to like make that algorithm work very efficiently. And in total, we have something like 41,000 nodes in that structure in the center that I've shown, and roughly 200,000 edges. So once this whole part here is completely learned from data. There's nothing that is hard-coded in a sense that there's no physical equation, nothing like that. So it's purely learned from data, and then once it's trained, you can essentially just push the data through process, and this is very, very easy and fast to do. So once you've done a 6-hour prediction, you can unroll the model auto-regressively, a little bit like traditional NWP work, and make a prediction up to 10 days, for instance. All right. So how did we train GraphCasts? So one of the key components of GraphCast is the training loss. And what we're trying to design the training loss for is to essentially penalize long-term error. So the loss term is essentially what we call an autoregressive loss that penalizes long-term error. And the way it works is that we essentially, with the parameter that we are trying to learn about GraphCast, we unroll a prediction over multiple steps. That number of steps can vary during the phase, during the training, and I'll explain how we do that. But we unroll that over several steps, let's say 2 or 3 steps, and then we compare that to the ground truth that is in era 5, and then we backpropagate the error through time. So it's called backpropagation through time. And so this way, we essentially learn the same model is applied several times to generate like multiple steps, but it's essentially penalizing the model in a way that when it makes the first 6-hour prediction, it's penalized if the error that it makes at this point is going to create more error at later stage. So it's essentially like it's a little bit akin to some of the techniques developed in reinforcement learning that try to kind of penalize or long-term error and do planning. So if I go into detail of the loss function, there's your typical kind of difference between what you've predicted with the x hats and your ground truth, which is era 5 in our case. We sum over the different forecast date time, so the initialization time of the data we're showing to the model. We sum over all of the different lead time, and that number of lead time can vary. So that's the length of the sequence that we're actually imposing loss on. We average also over all spatial location, and we also sum over multiple variable and levels that we're predicting. There's more terms. So this term S here essentially allows us to scale the different variables so that they're kind of roughly in the same range. So for instance, if temperature lives in a certain range of value and another physical variable lives in a different range, we're not forcing the model to learn temperature better than another variable just because the scale is much higher, and so the error would be much larger. So that term is essentially kind of scaling different variable and different level with respect to each other. This term W here is how we weight different levels with respect to each other, and this is purely a design choice. I'm showing here on the right like how we did it. This is, we just assumed that we would care more about the pressure level close to the surface because that's where humans live. So this is what we use. It's a linear weighting. So you can see that at low level pressure, the weight, so the importance we put on getting those variables right is much lower than for pressure level at very high value, for which we put a very high weight. So it's essentially saying we care more about predicting correctly the level close to the surface. And then here, this is like an area latitude longitude weighting, which essentially just weights the points at the poles, which the pixel represent very small area. So we weight those points less than the points at the equator, essentially. All right, so how do we train the model? There's 2 phases really in the training of the model. The first phase is doing a 1 autoregressive step, so essentially just a 1-step prediction of 6 hours. The reason we spend a lot of time on that, so we train the model from 0 steps to 300,000 steps on just 1-step prediction. And the reason is because it's faster to do that. Like it's just much more, there's less memory, it's less memory intensive, it's faster to train this way. And then the way you think about it is that compounding, if you're not doing a good job at predicting 6 hours, there's very little chances that you're going to make a good prediction at 12, 18 hours, 24 hours by unrolling your model. So we spend most of the time like focusing on getting the first step right before we shift to the second phase. And you can see in the second phase, where we spend like roughly 10,000 steps of training, we increase the number of autoregressive steps, the lead time of the sequence in that loss, from 1 to 2, 3, 4. We kind of ramp up to 12 steps, and 12 steps correspond to 3 days of forecast, essentially. So that's the part that we are supervising. We're supervising the training up to 3 days. And that part here is like quite expensive and requires a lot of engineering actually to kind of make everything fit on the device. All right. So there's another thing that we wanted to be very careful when we developed that model is that we were testing for the right type of generalization. So there's this thing in machine learning where you don't want to train and evaluate on the same data because you can fool yourself into thinking that your algorithm is working really well, when in fact you've overfit to the data you're training on. So you have to be very careful in general to kind of very strictly separating what you train on and what you validate on and what you test eventually on. And in the scenario where we're doing like weather forecasting, there's an additional kind of a concept, which is that we really want to be causal, in a sense that we want to train our model on past data, and our test of generalization should really be on future data, because that's the realistic scenario we're going to find ourselves in. So the way we approach that is to have two phases. The first one was the development phase. That's where we kind of like change the architecture of the model, which look for hyperparameter. We try to define what the training protocol looks like, the stopping criteria, all of that. So for that phase, we use data from 1979 to 2015 to train the model. And then when the model was trained, we were looking at the result on the validation set, which was 2016 and 2017. So we iterated that loop many times. Like I think for a year, we were working on that. Once we were happy with the result and we're confident in what we were seeing on 2016 and 2017, we froze the protocol. That means we made no new decision. Essentially, we had committed to a way of training the model, a way of building the model. So nothing really, we were essentially freezing all decision making. And we moved to the test phase. And in the test phase, what we did is that we reapplied the same protocol, but we used data from 1979 to 2017 included. So we just used more data, but nothing else about the protocol changed. The model was the same. The learning algorithm, the number of steps, the batch size, everything was the same. And once that was trained, we looked at the test sets and on 2018, and we reported the result. We were not allowed to go back to that phase where we iterate on the model. And actually, we went beyond that. If you've read the paper, you know that at some point we report results on multiple years and for different model retrain. We actually trained 4 models. The first one on data up to 2017. Another model we've trained from scratch with data up to 2018, 19, and 20. So we trained 4 different models completely from scratch. For most of the results I'll be showing today, it's the model based on data up to 2017, and we're reporting results on 2018. So all the results I'll be showing, except when I'm explicitly stating that I'm doing something a little bit different. So that's the reason we're doing that, is because most of the paper at the time were reporting results on 2018. So we wanted to be able to do the same reporting, but on being causal, as I explained in the previous slide. All right. So now I'm going to dive into some of the details that are in the paper about like how to make a fair evaluation against like the baseline, the traditional model HRES, which is a deterministic model. There's a lot of nitty-gritty details here, but I think they were pretty important to get right in order to make a fair evaluation, and I'll go into some of those details. So the question is what to use as ground truth, and it's quite a tricky question. So for GraphCast, we feed the model as input some ERA5 data, and that's ERA5 reanalysis. And when we make a forecast with the model, it's been trained to predict ERA5 analysis. So it makes sense to kind of use ERA5 as ground truth for that model. On the other hand, for HRES, this model is not initialized with the same type of input as GraphCast. It's initialized by something that is more operational analysis. There's a lot of nuances what that data is, but essentially the main point is that it's not the same thing as ERA5. So there's already one point of difference here, which is those models are not initialized in the same way. And the second aspect that we want to be very careful about is that if we wanted to compare a HRES forecast to ERA5, it's a little bit unfair because that model is not trained to predict ERA5 and is doing its own thing. So we wanted to make sure we're not arbitrarily penalizing HRES by making the wrong kind of comparison. So it turns out that we talked to a lot of people, including ECMWF, and what made more sense to use as ground truth for HRES is that data that we call HRES FC0. And I'll go in the next slide, I'll explain exactly what that is. So imagine it's midnight, you gather some observation, you've done your data analysis, your data assimilation, you get some initial state, that's the purple square here, and you unroll for HRES, or you make a forecast, and this is the forecast made by HRES at 6 hours ahead, 12 hours, 18 hours ahead. Okay, so that's your HRES data. Now, 6 hours later, you gather more observation, you redo your data assimilation, you get a new state, this new purple square here, and you unroll HRES again. And you can do that several times, all right? That happens every 6 hours. So what we use as ground truth for HRES is this data called HRES FC0, which is the collection of those purple states. So when, for instance, I'm considering this trajectory, this forecast by HRES, what it's using as ground truth to evaluate its performance is those purple square. They essentially represent kind of the refreshed states that has been kind of incorporating more and more recent observation. So it's it's a good grounded state, as we call it. And one of the property of doing this evaluation this way is that at lead time 0, your model has 0 error because it's comparing its own forecast to itself. So at short lead time, the model should not be penalized. And I'll show some results a bit later that shows like the impact of that decision. So there's another so that's one key difference, one key point on which we really paid attention in the paper. What kind of ground truths we use when we score those models. The second aspect is that we have to account for assimilation window and the look ahead there is in it. So I'll just go a little bit quick on this one, which is that ERA5 is constructed by using 12 hours assimilation windows. This means that all the states, between 9 p.m. and 9 a.m. are reconstructing using observation within that window. In particular, a state at 0Z, Zulu time, has access to information up to 9 hours ahead. And the state at 6Z has access to observation up to 3 hours ahead. So that means that in a sense, the state at 0Z has a look ahead advantage. It gets to see like more of the future when it's reconstructed. So if I were to feed 0Z to ERA5, in a sense, it's being fed an input that is of higher quality, that has been able to see more into the future, that if I'm feeding an input from 6Z, which has only seen 3 hours into the future. Why is this an issue? The issue is because HRES is initialized from something different, as I mentioned, and that initial state for HRES only has a 3-hour look ahead, right? So one thing we did in our paper is we never initialized GraphCast from the state at 0Z or 12Z, which are the state that have 9-hour look ahead. Instead, we always initialize HRES from 6Z and 18Z, so that the input it sees never has more than 3-hour look ahead. Right. So now the right thing to do is to initialize, ERA5 and HRES from those states and unroll the prediction and compare them. There's one more complication, which is that the forecasts from HRES are not recorded for 10 days all the time. If you look at the HRES forecast that is initialized at 0Z, it's, the forecast is unrolled for 10 days and this whole trajectory is stored. Same for HRES initialized at 12Z. But if you look at the forecast from HRES initialized from 6Z, it's only unrolled up to 3.75 days. So there's just no data stored after that. And so if you look at our paper, you might see this dashed vertical line. And what this means is that before that dashed line, we can actually compare to HRES initialized at the exact same time up to 3.75 days. But beyond that dashed line, we have to compare to a different initialization of HRES just because there's no other data available to compare to. You can see on the plot on the right, there's, it looks almost continuous. You might see some discontinuity, but the differences are pretty small. So this is how we try to do a job to be, as fair as possible when we compare to HRES. And just, maybe I'll mention that that's the result in the paper, but we've also kind of on GitHub put like an operational model. And if you see the forecasts that ECMWF is doing with GraphCast, it's a model that is a slightly different model that has been kind of fine-tuned on operational data, and it's initialized with the exact same data as HRES. So the live forecast that you're seeing on the ECMWF website are using, they're not initialized from ERA5. All right, so here are just like some visualization before I move to results. All right, so the first thing we did is look at aggregated score, we compare GraphCast to HRES, the deterministic model from ECMWF. Here you can see an example for one variable, the geopotential height at 500 hectopascal. So on the y-axis, you have the RMSE, lower is better. On the x-axis is the lead time from a few hours to up to 10 days. In blue, you can see GraphCast, and in black, you can see HRES. So you can see here that GraphCast outperforms HRES on most of the lead time, if not all, yes. And then below, I'm showing a relative plot, where the way to read that is basically the same information as above, but in relative plot. So what you can see here is that GraphCast is roughly 15% better than HRES at lead time 6 hours or 12 hours. And then roughly 7% better than HRES at 10 days for that specific variable. So that's just one variable. We can look at many variables. So temperature, the wind, specific humidity. I'll just draw your attention that here there's like one point where GraphCast is not as good as HRES. Actually, HRES outperforms GraphCast at temperature at the 2 meter altitude at 12-hour lead time. And that's going to be important in some of the next slides. And you can go even further. Instead of looking at just 4 variables, you can look at many variables for many lead time. And that's what we did in the scorecard. And the way to read the scorecard is that a row here represents a certain pressure level, 500 hectopascal, and Z means geopotential. And this line here corresponds to the plot, the relative plot I showed you earlier. So this is exactly that line, where when it's blue, it means that GraphCast is outperforming HRES, and when it's red, it means HRES is outperforming GraphCast. And you can do that for all the variables, all the pressure level we're computing, and all the lead time. And this is what the scorecard looks like, which, by the way, is inspired by what ECMWF is doing to evaluate their own model when they want to upgrade their IFS model. So one thing you notice is that GraphCast outperform HRES on 90% of those more than 1,300 targets. So it's blue on most squares. And the places where it's not as good is at high altitude, at low pressure levels. And you remember that when I talked about the loss function, this is where we put the less weight. So it's not that surprising. We told GraphCast when we trained it, don't care too much about the high altitude level. Focus on getting the high pressure level right. So it's not so surprising. And actually, in follow-up work, we've kind of trained to change that vertical weighting, and we can get that number up to 97%. I'll also point out that if you remove kind of the level that corresponds to the, I think, above the troposphere, so if you remove 150 hectopascal, then GraphCast outperforms HRES on 99% of those targets. So we also compare to some of the machine learning baseline. In red, you can see Pengu weather, which GraphCast outperformed on 99% of the target they published. You can see maybe one thing I want you to draw your attention to is that in black, you can see the performance of HRES against HRES FC0, which is kind of what we've been doing in the whole paper, to be fair to HRES. And in gray, you can see the performance of HRES when it's compared to ERA5. And you can see that, especially for a certain variable like the temperature at 2 meters, like if you compare your model and the baseline is HRES compared to ERA5, it's artificially penalizing HRES. So it looks like HRES is performing way worse than it actually is when you look at the black line. And for 2T, it's very, very clear that there's something wrong in making the evaluation in this sense. From some other variable, you can see that the difference between the gray line and the black line is mostly at early lead time, while at longer lead time is almost no difference. But that's something I wanted to point out, like the reason we were like so careful about evaluating HRES against this data set that we call HRES FC0. Right. So one thing that we kind of looked into after looking at the scorecard, which are like kind of RMSE numbered, but don't tell you necessarily much about like how useful the model is. We looked at severe weather application, and I want to stress out the fact that for that part, all the application I'm going to be showing, we didn't do anything special with GraphCast in its training. We just trained GraphCast in the way I've described, and there's no fine tuning. We're not doing anything special with GraphCast to use in those applications. There's no learning. There's no extra machine learning model on top of GraphCast after that. We just take the forecast and that's it. So the first thing we looked at is atmospheric rivers. And there's this quantity that people in the literature use to kind of characterize the strength of atmospheric rivers called integrated vapor transport, IVT. So this quantity is computed by non-linearly combining the specific turbidity with the horizontal wind, and it's integrating that quantity over multiple vertical levels. So in a sense, it's a non-linear combination and it's vertically integrated. And what we saw when we computed that quantity, just applying that to the GraphCast forecast and comparing to HRES, is that we also add an advantage. GraphCast also had an advantage over HRES to compute IVT. And you can see actually the difference, like you can get to the same level of accuracy of prediction of the strength of the atmospheric river, roughly like with a day of lead time, an extra day of lead time. So that's quite interesting. And we've seen like this month, like the impact of the atmospheric river on the west coast of California. So here it's just applying a nonlinear equation to the prediction of GraphCast. That's it, nothing more. The second application we looked at was severe weather and extreme heat in particular. And here we looked at whether from the prediction of GraphCast, whether or not you could classify if the temperature will be in the top X% of the temperature at a given location at a given time of the year. So we could say like, okay, is it going to be like more, extremely hot compared to the typical temperature in Italy in the summer, for instance. And so for that classification problem, we had essentially we applied just a gain to the forecast of the temperature with respect to the climatology, and essentially that parameter you get to choose, and that's what draws those lines, those precision recall curve here. So essentially, the takeaway from this slide is that the better model would be the one that lives in this corner of the plot with high precision and high recall. So here you can see GraphCast in blue and HRES in black for different lead time. And in light, you can see the short-term prediction, and in solid, the darker the line is, the more it's in the future. What you can see is that at 12-hour prediction, the black line dominates the blue line. So that means HRES is better than GraphCast at 2-hour prediction of extreme temperature. And that's kind of consistent with what I showed you in metric. Remember, I showed you that like at 12-hour, GraphCast had a lower RMSE error, had a higher RMSE error than HRES. So HRES was better. And that's consistent with what we're finding for the extreme temperature. For 5 days and for 10 days, what we see is that the blue line dominates the black line, showing that GraphCast is better at forecasting, being able to enable you to classify whether that temperature is going to be an extreme. So we did a study for 2%, 1%, 0.5%, and for different other temperature variable. And the picture was basically the same. So it's useful to essentially determine whether or not some temperature is going to be extreme. For the third application, we looked at tropical cyclone tracking. And for those results, because cyclones are fairly rare, we wanted to use more data than just 2018 data. So we looked at 4 years of data. So for 2018, we used the model causally trained up to 2017. For the result of 2019, we used the model trained up to 2018, etc. So all the data is generated in a causal way, and we aggregate the result over 4 years just because cyclones are fairly rare, and we wanted to be able to make statistical statements for which we need a large number of events. So what we saw as well here is that you can see the median track error in kilometer as a function of lead time for the position of the cyclone. And you can see here again that GraphCast has an advantage. The error bars are overlapping a little bit. So on the right, you can see a paired analysis. And you can see that the GraphCast is significantly outperforming HRES for the position of cyclone tracks from, I don't know, say a day ahead to 5 days ahead at least. And what I mean by statistically significant, I mean it in a statistical sense. So it's quite interesting and a good demonstration of how useful GraphCast is. I want to also show that the first time we open source GraphCast and ECMWF run that model on their website, there was this cyclone Lee. And GraphCast was able to predict that cyclone Lee would make landfall in Nova Scotia 9 days before the landfall, while traditional approaches essentially hesitated a lot and got only locked in Nova Scotia 6 days before the landfall. So that was a very being able to predict the track up to 9 days is not this is just one example. This is not what we had in the statistical evaluation that I showed before over 4 years, but this is still one real world example in which GraphCast really made a very good prediction. Yeah, so we've also shown that we can retrain GraphCast with fresh data. So for that experiment, I'm using the model trained over a different number of years, up to 2017, 18, 19, and 20. And all those models are evaluated on 2021 and compared to HRES from that year, 2021. So what you can see is a relative plot with respect to HRES, the black line. So when you're below the black line, you're better than HRES. And the model that is, 3-4 years old is outperforming HRES at most lead time. There's a little bit of loss of performance here. If you use the model that is using 1 more year of trained data, it's a little bit better. 1 more year of data even better. And the model that trained on the freshest data is the strongest. It's not a huge improvement, but it's a consistent improvement. So it shows that essentially those models should be retrained every year if you want to squeeze out all of the performance they can get. And the other takeaway is that you can use a model a few years old and the performance is still okay and pretty good and outperforming HRES. Right. So we did a lot of analysis. For instance, one question we got a lot is GraphCast getting a lot of performance because it's able to blur. And that's something we saw in the analysis is that actually, if you look at long lead time, the model is blurring its prediction, especially smooth. And that's something that is quite expected with deterministic models that are trained with RMSE loss. Essentially, the model is trying to avoid a double penalty, if you were to predict like something sharp, like let's say a storm at a certain location, and you got the pattern of the storm right, but slightly shifted, it would be penalized a lot. And so what tends to happen for those models that are deterministic and trained with RMSE is that they kind of predict something spatially smooth in order to reduce their error. And that's something we see here in those plots. So the darker the line, the further away in the future it is, and the lighter the line, the closer it's 12 hours of essentially lead time. The black line is the spectrum you should see from the ground truth data, and then the blue lines are the spectrum from HRS. And you can see that as you go further in time, certain variable becomes smoother and smoother. So we control for that in our paper as well. We basically applied, we're like, okay, is the performance of GraphCast only because it's able to blur and it's kind of reducing the error? So we applied a filtering, basically we control for blurring in our experiment for HRES. And what we saw is that the performance of HRES went from the black line here to the dashed black line here. And you can use the same type of blurring on top of GraphCast, and the performance go from the blue line here to the dashed blue line here. So essentially, like GraphCast was still outperforming HRES after applying that smoothing that can really improve performance by just tricking the RMSE numbers. I'd say that like this is an issue that we're trying to address in our subsequent model, that are probabilistic model. I don't know if I'll get to have time to talk about that, but we'll see what question we get. I want to point out that the model is on GitHub, so people can just, like a researcher can write paper about that, use the model freely, or look at the code and how it works. The forecast is available on ECMW websites. It's making live prediction. So the version of the model they're running is a model that is slightly different than the one in the paper. It's been kind of fine-tuned to work with operational data. So we are not feeding it ERA5, but it's fed the real live inputs that HRES is getting. And finally, before getting questions, just some conclusion words. GraphCast outperformed the best deterministic model that is operational on 90% of 1,300 targets. If you remove the top part of the atmosphere, that number is even higher. It's useful for a real-world application. We've seen cyclone tracking, but there's other applications such as quantifying the strength of atmospheric rivers and extreme temperatures. It's really fast. I haven't mentioned that, but making a 10-day forecast with GraphCast takes a minute on a specialized chip that is called a TPU v4. It's essentially a chip that is this size, and that you can make a forecast in 1 minute with that. And with the newest generation of ML chips, you can even bring that to 30 seconds. So it's really, really fast, and the chip is really small. That's compared to like the order of magnitude of hours on a supercomputer for traditional approaches. There's still more work to be done. Like the deterministic model, as I mentioned, or trained with RMSE, like they don't fully characterize the prediction uncertainty, which is something really important when you're talking about extreme events. And it's also very important in many applications that the forecast is not smooth spatially, but you get very sharp features. So I'll draw on that point. I'll draw your attention to a paper that we've recently put on arXiv. It's preliminary work at lower resolution, and the model is called GenCast. It's a probabilistic model that can generate a full ensemble of prediction. It's based on diffusion model, if you're familiar with that in machine learning. And finally, I think I want to reemphasize that deep learning really, and machine learning and AI really brings like a new way to improve the weather forecast. And it's by shifting the mindset from putting more compute and resolving things at higher and higher resolution. We're shifting from that paradigm to being able to leveraging more and more high resolution data and high quality data to improve the forecast. And with that, I'm happy to take any question you have. I'm at 45 minutes, so that leaves a little bit of time for question. So yeah.
Fantastic. Thank you so much, Remi. Really appreciate you taking the time. It's really, really exciting work. We have a whole bunch of questions, so sure. I will only use my facilitator privileges to ask you a very specific question, which is what precision did you have in your TPU? Like, is it 64-bit, 32? What's the precision of the numbers?
So all the evaluation are run at float 32. So everything, when we compare to ground truth, it's always at float 32 precision. But inside the model, there's different parts. Certain parts are run at float 32, but a lot of the arithmetic is actually run at lower precision, something called BF16. It's like it's just a format. It's float 16 with like a few extra bits here and there. And it's actually a lot of the tricky part is where to use that lower precision to make sure that your algorithm is still stable. So you don't want to lose the stability, and you want to be able to kind of reduce the memory footprint of your own algorithm. Because the data is so big, you don't have that much space for the model. And that's something I actually mentioned in the presentation, is that GraphCast only has 37 million parameters. It's tiny. Like when you think about when the deep learning revolution started in 2012, that was started by a model called AlexNet to do like some recognition essentially. That's like from 10 years ago, more than 10 years ago. And GraphCast has half the number of parameters of that model. So it's a very tiny model, but the challenge is to deal with the very, very large input and data.
Wow, fantastic. All right, so we have a bunch of questions. So what I'm going to do is I'm going to read them, and then if you could try and sort of keep your question, your answer to a couple of minutes, we might be able to get through all of them in 15 minutes. So I'll stress my English and go as fast as I can. So one understands that the Earth's surface is prioritized in formula and machine learning. However, the upper levels are very important, say at 500 millibar heights. Sometimes bad weather happens due to so-called cover flows or cold pools at height with little identifiable features at the Earth's surface, and that's where weather forecasting has to be improved the most. I would add, by the way, that I noticed you didn't have anything about precipitation as a kind of variable. So if you answer that question with this idea of physics, where's the physics?
Yes, so we're not weather forecast experts, so I think we kind of that decision about how to weight the vertical level was kind of fairly arbitrary, and it was just like, okay, let's not tweak too much those parameters because we don't want to be doing that, and we don't know exactly what matters the most. I would say it's like, as I mentioned during the presentation, like we've been able to change that weighting to put more emphasis on the higher level in the atmosphere, and we can get them better. So I think this is more of a design choice. Like you can choose to design your model for certain part of the atmosphere being better captured. Ideally, we'd like to have a model to rule them all and to be like best at everything. But that's something, if you care about certain lead times or certain part of the atmosphere, you can train the model specifically for that. For instance, if you care about making a forecast up to 12 hours because that's what you use for, I don't know, data assimilation, and you care about the higher part of the atmosphere, you can do that. You don't have to use the 12-step autoregressive. You can do like 1 step, 2 steps, and put a lot of weight in the part of the atmosphere you care about. So I think this is kind of like actually a strength of those models, is that they allow you to kind of decide what you want to be good at, and it's very flexible. And the fact that non-expert can like have very good model in a very short amount of time is like telling you how easy it is to kind of adapt this model. Second part of the question about precipitation, we do have results in the appendices of the science paper. They're publicly available, so I encourage you to check them. One reason we didn't include them, I mean, we didn't do anything special about precipitation. We actually predict precipitation, but we didn't do anything special. We know we can improve the results by like taking doing log transform. We didn't do anything special, but we still predict it. The reason we're not reporting it is because there's no, essentially, like we couldn't construct a dataset HRES F0 with precipitation in the product that is available for HRES. There's no precipitation at the first step, and so the protocol for evaluation is completely different, and we have to compare HRES to RFI, which is a little bit unfair. So we didn't make any scientific claim about that, but the results are in the appendices if you're curious. We're just not making any sort of statement about that.
Great. Thank you. All right. Adam asks the following. Hi, Remi. This is very exciting. Offers great promise for revolutionizing forecast production. We're following a similar path informed not least by your work at my institute, the UK Met Office. Can you confirm if GraphCast can forecast out of sample events like new record temperatures? I imagine it can, but some people argue defensively that this may not be the case.
I'm sorry, could you repeat the question, the second part about?
Can you confirm if GraphCast can forecast out of sample events like new record temperatures?
Yes, that's a really good question, and I think this is something that require more work, and that's verification, and that's one of the reasons we made the forecast and the model publicly available, is that expert can look at that and assess that. We're not experts to look at specific events and how extreme events occur. So that's one reason we've put the model out there so people can look for them, and we kind of help ECMWF put the model on their website. So that's the first aspect. The second aspect I want to say is that as I mentioned in the kind of retraining the model, we can retrain the model, and we can see that the performance improves when you retrain with the freshest data, essentially. So I think, like you're an institute for climate modeling, that model cannot be used for climate projection. But I think what gives me hope is that essentially when there's new trends in medium range forecast because of climate change or whatnot, we have essentially a mechanism to kind of adapt the model as we go. So I think it's very unlikely we'll have a model that will use 5 years without retraining it. It's becoming cheaper and cheaper to retrain them. So essentially what will happen is that we will take the freshest data, retrain the model, and as long as those extreme patterns or we see that in the data, I think the model should be able to adapt. But the question of whether or not you'll be able to predict like 1 in a century type of event, I think this is like quite an open question, and I would expect you would need something like a probabilistic model to capture these events. Not the deterministic model will probably have limitation there.
Fantastic. So Christopher asks, in your graph neural network, do you use weight sharing or some other method that reduces the number of parameters in a similar way to weight sharing? One of the strengths of convolutional neural networks is that it makes use of weight sharing, and I think it should be possible to do for your GNN2 in some way or something similar to it, but I can't find any mention of it in your article.
Yeah, it's all in the appendices. There's a ton of weight sharing. Essentially, it's the same function applied everywhere in space, and that's how we get to 37 million parameters and not way more. So yes, I actually, if you are interested in the appendices, I would encourage you to go on the blog post of DeepMind. At the bottom, you have access to like a free version of the science paper, and there's also like our own version of the PDF that has hyperlink, which is very useful if you want to navigate the more than 130 pages of appendices. But I can guarantee all is explained in there, and then the weight sharing is also in the code, so you can check on GitHub, so you can see how it works.
Fantastic. It must have taken you a long time to write those appendices.
Yes.
So Giangiacomo asks, hi, Remi, I have a couple of questions. Is GraphCast a completely data-driven model? I mean, you haven't inserted in the training a constraint given by a physical equation. This is a question I've seen coming from many people in earth science. Two, recently another model that is coming out is GenCast. What is the difference with GraphCast?
Yes, so there's nothing physical, there's no equation, we don't impose anything, pretty much we learn everything from data. For instance, like even precipitation, we don't impose that quantity needs to be positive or anything like that. It's really like we just let the model learn from the raw data. So I think the mention here is GenCast, which is a paper we just put on arXiv on December 25th. GraphCast was a year before on December 24th. So those are the people that work on that project. And essentially, like what GenCast is a diffusion model. It's an ensemble model, and you feed it some inputs and some noise that you generate on a sphere. That's very easy to generate, and then the model essentially kind of denoise that noise in order to make the prediction at the next step. And because you can generate noise in multiple ways, you can generate a full ensemble of trajectory that are not physically consistent, but that are like coherent over time. So essentially, we're modeling the joint distribution over space and time with that model. That type of model is called a diffusion model. I don't really have time to go into the details. Maybe one highlight I want to be able to show here is that this is the prediction at a specific validity time with a model with GenCast initialized 12 hours earlier. You can see that this is the ensemble mean of the 3 samples from GenCast. They all kind of look the same because it's close in the future. And this is the ground truth on the left. And on the right, you can see GraphCast, GenCast ensemble, and 3 samples from GenCast. And here is the ground truth. And at the bottom, you can see the same validity time, but from a prediction that has been made 10 days earlier. You can see that each sample from GenCast is different. There's a lot of variety, like in the same way you would get from an ensemble. The ensemble mean doesn't capture nearly as well the position of the cyclones. And then you can see GraphCast on the right that has a very smooth prediction, while GenCast is very sharp, it's not smoothing over space. So I think this is kind of the main difference. Like GenCast is a generative probabilistic model, while GraphCast is a deterministic model. And GenCast so far is operating at 1 degree resolution, while GraphCast is operating at 1/4 degree resolution.
Great, thank you. So Enrico has 2 slightly lengthy questions, so I'll read them to you. Thanks a lot for your talk, Remi. A couple of questions. What do you expect training your model with all products such as ERA 15, circa 1995? Can we expect a proportional improvement compared to the most accurate operational deterministic systems of the 90s only, or do you expect to perform also get closer to state-of-the-art in 2024 operational deterministic systems? Assuming that improving, for example, with higher horizontal resolution, reanalysis used to train plays a role, how far is the saturation? In other words, to which extent it is important to continue to improve reanalysis products? Emily, pause there.
Okay, that was a quite long question. There's part of the question I didn't get, so I'll focus on the last part. I would say for machine learning algorithm, the quality is the quality of the data is the most important thing, and the quantity of it. I'd say like we tried also to look at like past data before 1979. We didn't see any improvement. I think it's because maybe there were not that many observations back in the day, so the quality of data is maybe not as good, or it's not as relevant for the type of prediction we're seeing nowadays. But the quality of the data in itself is like the most important thing. And I think I didn't get to touch on that, but that's the fact that we're training on reanalysis and not just reforecast is how we get better than H-res, because the targets we use to train the model then get the benefit of having observation integrated in them, and that's how we get better essentially. So I would say like if we get like better reanalysis product in the future, that should help the model. But I think we're going to see a slew of different models that learn directly from observation that can go even at higher resolution. Radar data is at what sub-kilometer resolution. Satellite image is also pretty high resolution. So I think a combination of like those better reanalysis, and observation data is really going to be driving the performance going forward.
Great. So Madi asks a simple question with probably a difficult answer, which is, can this method be used to predict phenomena such as NAO or ENSO?
So I've only heard about ENSO, so I would say the timescale is a little bit longer than what the 10 days were predicting. GraphCast is really designed to work up to 10 days, GenCast up to 15 days. So I don't know. I don't know, like the performance past that to make a prediction for I don't know, ENSO or any other pattern that is much beyond that, I'm not quite sure. There's a question about where for a model that has only seen, let's say, up to 3 days at train time of data, what kind of frequency that can it capture correctly? You have all this Shannon theorem about like the aliasing and everything. Like there might be some limitation, or you might need to train a model that sees more lower frequency content in order to capture those patterns, right? So this is quite an open question. I don't know. I think there's other type of model we'll see that will go to longer horizon in a skillful way that can be used, that will be able to predict those patterns, especially when it comes like to, I don't know, I have very poor understanding of how those phenomena work, but I keep hearing about teleconnection and things like that. And I think this is something an algorithm like machine learning can like pretty pick up on, that the traditional model will pretty like struggle a bit more with.
Wonderful. And then I think we may have just one last question. So Stefano Tibaldi asks, thanks for a nice talk. The model seems to have lower performance at a very short range, 6 to 12 hours. Will this prevent its usage to replace conventional models also in data simulation?
Okay, so there's another ablation in the paper, which is the number of autoregressive steps. And what we've shown is that essentially there's a trade-off with the current model on if you want to get good long-term performance or shorter performance. When you train autoregressively over multiple steps, the model kind of loses a little bit of performance at short lead time in order to really improve the performance at longer lead time. So you can see the ablation in the paper. You see the curve like of performance kind of tilting essentially. So if you really care about short-term performance, you can just train a model to predict the next 6 hours, 12 hours, and not auto-regressively train up to 3 days, and you will recover some more performance at short lead time. That being said, I think, I don't know exactly what the timescale you need for that assimilation. I think it's like, I guess, up to 12 hours or something like that. And I've also heard that like higher part of the atmosphere are important for that. I think it's really possible if you have the raw data at the resolution that is relevant for your program to train a model specifically for that.
Great. And then the very last question, Antonio asks, do you have plans to validate the model with actual ground-based in situ observations in addition to the ERA reanalysis?
That would be amazing, but getting raw observation to validate against is actually pretty difficult. But that's ideally like one thing like we'd like to do. I think that's something ECNWF could do very easily because they have access to the data and the model is in their hands at this point. But for us, yes, that's the question is like, how do you do evaluation and how do you make sure that you can have global coverage, because we don't have observation everywhere in the world, and we don't want to specialize the model to be overly good over Europe and then neglect other part of the world, right? So I think this is an open question, but if you know about open source or data, observation data that we could be using for evaluation or even training, that's something would be like very interesting to cover.
Wonderful. So I'm afraid this is all we have time for. So Remi, we'll make sure to send you all the other questions to show you know what people were interested in. And thank you everybody for asking the questions. Apologies if we can get to all of them. But again, Remi, thank you so much for taking the time. This is really extraordinary work, and we're all very excited to see how it develops. So thanks for joining, and thank you, everybody, for taking the time. See you next time.
Thank you for the invitation. Thank you for the question.
Bye-bye.
Bye-bye.